to talk about PID loops. PID loop is a type of feedback loop, so I think before we get into PID, I want to talk briefly about what a feedback loop is. In a feedback loop, you have a sensor that is monitoring a position of something that is controlled by an actuator. And what I mean by sensor and what I mean by position and what I mean by actuator, I mean in very loose terms. Your position might be a temperature, your actuator might be a heater, and your sensor might be a temperature probe. So you've got the temperature being read by the probe, which is then going through your PID loop, your feedback loop, controlling the actuator, which is then changing the temperature, which then you're reading with the temperature probe, which then is changing the temperature with the heater, and you've got this continuous feedback loop as you're sensing the temperature, changing the temperature, sensing the temperature, changing the temperature. And as you're doing that, you're trying to move towards a goal. And you would be doing the same thing with laces, like say an arm. You've got an arm and you want the arm to be here, and you're sensing its position, say with on the angle. So you've got a sensor that's checking the angle, and then you've got a motor. So as we're moving towards the goal, we're sensing the angle, we're changing the angle with the motor, and we're sensing the angle, and we're changing it. So what we have is we have a goal, and we're subtracting from that goal the position, and that gives us the error in the system. So like if I'm at 90 degrees, I'm trying to get to 120 degrees, I subtract 90 from 20, and then that's my error, and that error as I'm moving gets smaller and smaller and smaller. Okay, so what we would do is we take that error, we have a mathematical function.
Ooh.
And that mathematical function we're going to output that to our actuator. And the actuator is going to change our position, which we're going to then recalculate the error, and that's going to go back into the function. Back in the actuator makes a change. We see the change, make the change, see the change. It's just an infinite loop, and it keeps running forever until we tell it not to. And that is the basics of a feedback loop. That's the foundation for this talk, so we need to understand that. Anybody have any questions just about feedback loop?
We would want to stop it when error equals 0, I presume.
Yes, but you might be, well, for example, let's say you've got a koi pond and you're measuring the temperature and you're trying to keep that temperature. Well, just because you get to the point where you have 0 error, you don't want to suddenly shut the system off because, well, nighttime comes and then it gets cold again, or a cloud comes over and your koi pond starts getting cold. So even though you get to 0 error, you want to keep the system running because whatever got you away from 0 error could come back.
Or if you're fighting gravity, I mean, you might get 0 error, but you still have gravity, and if you shut it off, then gravity will pull it away.
Right.
Good point.
Or if this is your line follower, you're going to get your robot back to the line, but then you're going to come to a corner, and you're going to have to track that line again. So typically, your feedback loop runs continuously until you shut your robot off or your system off. It's like your heating and air conditioning system. Your thermostat is constantly sitting there on the wall, monitoring the temperature of the room, and turning the heat and the air conditioning on, depending on whether you get outside or inside 0 error. Any other questions on feedback loops? Okay. Because I need the board. Okay. All right. So. Now, let's use an example. I'm just going to use a typical example we use. We're going to do line follow. So here's our line, and we're looking down at the line. And then here's a typical robot, very similar to, say, the 3Pi. You've got 5 sensors, and you've got 2 wheels, and each wheel has a motor. Okay. Let's just say that's the right motor and the left motor. And these sensors send a signal to your microcontroller, and it's going to give you a value as to where the line is. And let's just say this particular sensor, when the line is all the way over here, it gives a 0, and when it's all the way over here, it gives a 6. So in the middle, we're at 3, and it gives us all the points in between these two, or at least a lot of points in between. So our error is going to be our goal equal to our goal, which is 3. We want to be right in the middle, minus the reading we take from the line sensor. So we're going to call the line sensor. We have a function called line sensor. We call that, and that tells us where the line is. We subtract that value from 3, and that's our error. So if we're at 6, we would have 3 minus 6, which would be negative 3. So our error would be negative 3. Everybody got that? Okay. Okay. Now what we would want to do is we would want to feed that error to the motor. So we make a call to our motor controller. So we would have motor right, speed, and we would feed that our speed plus the error. And then we would have another call that we would make to the other motor. Motor left, speed, minus the error. And we would have like a variable up here called speed, where we would set the speed. And let's say these motors expect a value of, say, 100 would be full forward, 0 is stop, minus 100 is full reverse. And let's set our speed to somewhere in the middle of that. Let's just say 50. So we're putting 50 and 50 here, and if we had 0 error, then each motor would be doing 50, and our robot would just go straight. And if we have error, we're going to subtract that error value from one motor, and we're going to add it to the other motor. So for example, if we were at the 6, and our error equals minus 3, right? We've got the 3 minus 6 equals minus 3. So what we would be doing is we would have the speed value here would be 50 minus 3, so that would be 47. And then down here we would have 50 minus a minus 3, which would make the minus plus. So we would have 53 here. So that would cause the robot, let's see, the right motor would be going a little slower, and the left motor would be going a little faster, so that would cause us to turn this way, right? And that's where our line is, so we're turning towards the line. But if you think about it, that's a very small difference between them. You know, the speed of 50 versus the speed of 53, that's very small. So, and 6 is our maximum value. So we probably want to turn it a little harder. So what we actually want to do is we want to have the value P, or say the error, we have a constant called P, we multiply that times the error P does is it allows us to adjust how much we want the error to affect the speed. So if it turns out that we're really not turning hard enough, what we do is we turn up the P. We increase our constant here so that we get more turning. But it could be a case where we need less turning. If in our call here, if this is expecting much smaller numbers, then we could use this to turn it down. So the KP allows us to adjust how much influence the error has in biasing our speed. This error term here is a bias for the speed. Everybody understand that so far? Okay. Okay, so what we have is the more error we have in the system, the more P we have. It's proportional. Proportional to our error is now proportional. Our value going to the motors controlling is proportional to our error, and that's what the P in PID stands for, proportional. It's our proportional response to the error that gives us a bias to our control. So, where's your go? Okay. Let me change that. We now have P here. And like I was saying, we probably want that to be a little bigger. Let's say what we really want is for the bias here to be something more like 10. So what we really want is when we're at 3, when we're at the maximum error, times the constant equals 10. So we're really looking at a K of 3.33. So now our K is 3.33. So when we're at our maximum here, we're outputting 10 and 10 instead of just 3 and 3. So that's just an example. We'd have to actually put it into the robot, try driving it around, see if that's going to work. Okay, now there's more information we can get from the data. If we graph the data, if I were to take the robot and I were to just move it back and forth and we were to plot that data, we would get a plot similar to this. This is our time, and this is error. And I just do this, you would see something like that, right? Everybody get that? This is 0 error, and this is positive and negative error, and this is time. So as I'm rotating through there, the sensor's sweeping across the line. We're getting more error, and then negative error, like that. And right now we're getting a proportional response to that. The more error here, the more of a response we get. But what if when the robot was trying to control whatever it's trying to control, whether it's your temperature or an arm, if that arm got stuck and wasn't able to move anymore, what you would have is a constant error. That shows we got stuck. In other words, we got to a certain point and we're continuing to get the same value. We'll get the same response. If the error is constant, our bias is constant. And let's say the robot's trying to get up a hill. If that's not enough to get the robot, if that's not enough voltage to the motor, or if let's say you're trying to heat a pond, if that's not enough voltage to heat that pond, then you're never going to get back to 0. You need some way of saying, I'm stuck, let's increase the voltage. And you can't get that from just looking at the position. If we're just looking at the position, well, the position, our error, is constant. So what is changing on the graph that we could, does anybody see what is changing on this graph?
Time.
Hmm?
Time.
Time, well, time is always changing, but that is kind of,
Length of time.
hmm? But that is a component of it. What is actually changing here is the area under this curve. Because once that falls to 0, well, the area under the curve falls to 0 too. So what we have is area under the curve. We can look to see, is the area under the curve continuing to grow? And that is our I term. So what we want to do is we want to take the area. Now that I've drawn like little stripes, it's kind of hard to see what I'm doing, so I'm going to go redraw it. So we take, each one of these points is a loop. So each time we take a loop, we can get an area, and I'm just going to draw one of these little rectangles down here. So each time we take a loop, this is the time base here. So this would be our loop time, and then this would be the error. So to get the area of this little piece of the area under the curve, it's just the error times the loop time. Because when you're taking an area of something rectangular, it's just the base times the height. So what we're going to do, and we want all of these. So we want, for each loop, we want to add them all up. We want the entire area, not just each individual area. So what we're going to do is we're going to accumulate all of those little rectangles into I. So we're going to say I equals I plus each of those little areas. So now, let's say the area, error, minus the last, sorry, I got ahead of this, loop time. And we still want a constant. This is going to be a different constant. This is going to be Ki. We want that to be separate from this one. That way we have an adjuster for this term, and now we have an adjuster for this term. And that's all Ki is. It's just like here we wanted to be able to adjust it. Here again we want to be able to adjust how much I is influencing our feedback loop. So we've got the area for each one of these little rectangles being loaded, being accumulated into our variable I. And sometimes the I term is called the error accumulator, because that's exactly what it's doing. It's accumulating all of the error that we're seeing in our loops. So the I term will grow larger and larger and larger the more we stay on one side of the line. As soon as we go to the other side of the line, those rectangles would subtract out of this. So as long as we stay on one side of the line, this will continue to grow, and it will grow until it can't grow anymore. It will grow until we hit the maximum value allowed in our motor control. So if your robot's motors, or if the heater for your pond, or whatever you're trying to control, if it is strong enough to get you unstuck, you will eventually get unstuck. But there's also a danger there. That maximum value for the motor might also be enough to burn it up if you're stuck and you don't get unstuck. For example, if this robot ran into a wall and the I term just said, oh, I'm stuck, and it started running those motors, running the motors, running it all the way up to 100, I would be putting the maximum amount of voltage into my motors, but I'd be up against a wall, and I'm never going to get unstuck. So when you're using I, you have to watch out for the possibility of overrunning your motor, overrunning your heater, and that sort of thing. This term will just continue to grow and grow and grow if you get stuck on one side or the other. The I term is a very important term if you're worried about getting stuck, if you've got a lot of friction in the system. But if you don't have a lot of friction in the system, if you're not that worried about getting stuck, the I term is actually rarely used. Yes?
I want to comment about that. Instead of the getting stuck paradigm, which I'm not sure happens that often,
Right.
the I term is mostly used to make sure your error can always go to 0. If you're going in a circle, your line is a circle.
Right.
In order to move in that circle, you've always got to have some error to steer your wheels, right? Otherwise you go straight. So you're always going to have some error. You're not going to be on the line exactly. You're going to be off the line a little bit in order to make the circle.
Right.
If you have the I term in there, it's going to integrate that error and make you stay right on the line even though you're going in a circle.
Right.
And that's what it's mainly used for, at least in my opinion.
To keep you from getting off, going back, getting off,
Yeah, in
going
other
back,
words,
getting
in
off.
order
It
to
kind
make
of
the circle, you
smooths
might
it
have
out.
a constant error of, say, -2 in order to do the circle.
Right.
And that means you're skewed a little bit, you're going off the line. But if you have the I term in there, it'll integrate and bring that term back to 0 again,
Right.
while actually putting a differential on your motors.
Right.
Your motors see an error term, or they see drive, but there's really 0 error. If that makes any sense. I'm not
Okay.
explaining it exactly right.
Another example I was thinking of, maybe, do you agree with this, is it would be like if your robot's running on a hard surface, but then you get up onto like a deep pile carpet, it would be good to, the I term would be good to try to get a
Yeah, if
smooth
you're trying to regulate your speed. Because in order to maintain 0 error, you would need more, well, yeah, I guess that would
Yeah.
You need more power.
you need more power to run at the same speed,
Right.
and thus more error, but like, I'm not sure that would actually apply.
Mm.
Proportional would take care of that.
I think proportional would take care of that. But the example of going in a circle, I think, is the most, the best example I can think of.
Right.
You do have to have a differential on the motors, but if you have 0 error, you won't have a differential on the motors.
Right.
Unless you have an I term, right? You would.
Okay. I have noticed though that the I term is kind of tricky to.
It is.
It is very tricky.
Very hard to tune that one, correct.
Yes, it is. I would start out very, very small. Work your way up. Okay. So, if we're looking at the data, let's go back to just looking at the data. We can get a proportional feedback from just looking at the position. We can look at the area under the curve, but we can also look at this, at the idea of how much the error is changing per unit time. For example, between here and here, the error is rapidly increasing, while between here and here, the error is pretty much steady. And then between here and here, the error is rapidly decreasing. That's very powerful information because, for example, here we know we're rapidly approaching 0. So that would be like if you're closing a door and you realize you're almost about to close the door, but the door's moving really fast. I'm sure we all do this almost every day. You're closing a door, and it's a big heavy door, and it's moving kind of fast, and you're getting near the door jamb, and you realize, if I let the door keep going like it's going to slam. So you pull back on that door. You were pushing the door, but now you're pulling back. Well, that's exactly what this will allow us to do. We'll see that we're quickly approaching where we want to be, so it's time to pull back. And it also allows us to do the opposite. When we see that we're quickly moving away from where we want to be, we can pull back. So that's what the D term is going to give us. So the D term, we calculate it just by looking at by calculating the velocity, which is just the slope, which is just rise over run. So on the rise over run, so we've got the rise is just the difference in error of the 2 points. So we would have the error and the last error, and then the run is just our loop time again. So all we need to do is, well, we're going to start out again with a KD. We're having another adjuster here, so we can adjust how much D term we use. And then we're just going to have the error minus the last error, the error from the previous loop. And that will be divided by our loop time. Okay. All right, and we needed to be having I term here, D term here, I term here, and D term here. Okay, so now we have PID. So our full PID routine here is being subtracted and added for our motors. Okay. Now that we've pretty much, this is pretty much it. This is written in Pseudocode. I haven't really decided, I haven't really written this for any particular microcontroller. This is just Pseudocode that you could use, you could adapt to any programming language depending on what microcontroller you're using. But this is pretty much all you need. You'll need to store your error, just for completeness, let's say last error equals, this loop's error. You're going to want that. You'll also want to somewhere in here be calculating your loop time, how much time between each loop. I typically use about 50 measurements per second, so I'm usually at around 20 milliseconds per loop. So now I'm just going to talk about some general gotchas, some devils in the details kind of thing. For one thing, PID is not a filter. You have to do all your filtering before you get into your PID loop. In other words, in the call that you're making to your sensor. In this case, we're making a call to a line sensor. This could be your call to your temperature sensor. Whatever is feeding the data into this loop, that is where you have to be doing your filtering. Any error, any noise in the system, the PID loop is going to see as actual data. So if you've got the occasional blip or a lot of noise, that will be reacted to by the PID, and certain members of the PID will react more to certain types of noise. For example, the occasional blip will be seen as a big change in the velocity of the air, so the D term will get real excited by occasional blips. But you definitely want to get all your filtering done here. And let's talk a little bit about tuning. I showed you how to get a decent starting value for K. When we, in this little equation here, we were just looking at the minimum and maximum values coming in to the system, and then looking at the minimum and maximum values coming out of the system. And from that, you can kind of decide about how much you want the maximum value to offset your actuator, and that would just be a starting point for this value, and you would